Welcome to The Explainer. So, today we are diving straight into something totally mind-bending. Deep out in the cosmos, a recent discovery about pulsars has literally just shattered decades of established astrophysics. If you thought we had these rapidly spinning, dead stars completely figured out, well, you're in for a massive surprise. We're going to unpack exactly how this new data is completely rewriting the rules of the universe and breaking down how this complex cosmic phenomenon actually operates.
Here is our roadmap for today. Number 1, the cosmic lighthouse myth. 2, the violent death of a star. 3, extreme density and speed. 4, the earth-shattering new discovery. And 5, a boon for astrophysics. Let's get right into it.
Section 1, the cosmic lighthouse myth and decades of established science. Before we can break the rules, we kind of need to know exactly what they are first.
For decades now, the classic textbook model has portrayed neutron stars pretty much exactly like a cosmic lighthouse. The idea was simple. As the star spins, it shoots out these tightly focused beams of radiation exclusively from its magnetic poles. And when one of those beams just happens to sweep past Earth, boom, our telescopes pick it up as a pulse. It's a really neat, elegant model. But, as we're about to see, it's definitely not the whole picture. Moving to Section 2, the violent death of a star and the birth of a neutron star. To really appreciate how wild this new discovery is, we have to ground ourselves in the sheer chaos of how these things are born. Pulsars don't just gently fade into existence, they are forged in absolute destruction. Just as a quick recap of this violent process, when a supermassive star finally exhausts its nuclear fuel, the outward pressure stops, and gravity instantly takes over. The core collapses in on itself, the outer layers violently rebound in a spectacular supernova explosion, and what's left behind is the neutron star. It's basically the universe's most extreme recycling process. Section 3, extreme density and speed, looking at the physics of the core. Now, the physics of this surviving remnant are where things get truly mind-boggling, pushing the boundaries way beyond anything we could ever replicate in a lab here on Earth. Millions of tons. Seriously, think about that. When that star's core collapses, the matter gets compressed to an absolutely unbelievable degree. The pressure is so intensely overwhelming that it literally crushes the electrons and protons of the atoms together to form neutrons. Because of that, this resulting object is so incredibly dense that just a single spoonful of it would weigh millions of tons if you brought it to Earth. A single spoonful. And this ultra-compressed, layered interior doesn't just make the star insanely heavy, it also generates some of the absolute most powerful magnetic fields known to science. It is this bizarre, extreme environment that actually lets astrophysicists test theories about fundamental forces that, honestly, we just couldn't study anywhere else. But hey, density and magnetism are just part of the story. We also have to talk about speed. As the star collapses and shrinks down, its rotation drastically accelerates. Think of an ice skater out on the rink. You know how when they pull their arms in tight to their body, they spin faster and faster? Well, this dying star is doing exactly that, just on a massive cosmic scale.
Which brings us to this staggering number. Hundreds of revolutions per second. Hundreds. These incredibly dense, ridiculously heavy spheres are whipping around in space at blinding speeds. It is a violent, churning, hyper-fast environment. And it's exactly this extreme speed that sets the stage for the big breakthrough.
Section 4. The earth-shattering new discovery. Breaking the rules. This is the moment where modern astronomical data comes in and completely shatters that old, neat lighthouse model we set up at the beginning.
So scientists looked at about 200 fast-spinning pulsars, comparing radio observations with gamma-ray data from NASA's Fermi Space Telescope, and a totally stark pattern emerged. They realized that for a full one-third of these fast-spinning objects, the radio waves weren't just coming from the poles. They were coming from 2 or more distinct zones around the star. But when they looked at slow-spinning neutron stars, only 3% did this. The huge takeaway here? This rich multi-zone emission is directly linked to how fast that pulsar is spinning. I mean, this really changes everything. The old model rigidly confined those emissions to narrow polar cones, our lighthouse. But the new data proves that these pulsars are actually emitting radio waves from a swirling current sheet of charged particles located way further out from the star. The lighthouse isn't just shining a beam from the very top anymore. The whole thing is practically glowing from this turbulent storm whipping around it.
Section 5. A boon for astrophysics, and why this matters. Now you might be sitting there wondering, okay, sure, that's a cool detail, but why does it actually matter to us? Well, the consequences of this are literally universe-altering.
Because these radio waves are coming from those swirling outer sheets and not just the narrow polar beams, they are being cast out in much, much wider directions. A pulsar doesn't need to be perfectly magically aligned with Earth for us to spot it anymore. This wider net makes detecting these millisecond pulsars so much easier, and finding more of them is a massive advantage because astrophysicists use vast networks of these pulsars as ultra-precise instruments to measure and track gravitational waves rippling through space-time. This literally upgrades our cosmic toolkit.
But as with all great science, answering one question just opens up another massive unsolved mystery. As the authors highlighted in their study and the monthly notices of the Royal Astronomical Society, we still don't fully get the exact mechanism here. Like, by what process are these radio pulses actually being created so far away from the star, out in those highly agitated swirling current sheets? Figuring out that specific mechanism is our next major hurdle to fully utilizing these objects.
Which leaves us with this final provocative thought to end the explainer on. If an established, decades-old scientific rule about pulsars can be so thoroughly expanded just by looking a little closer at the data, how much more of the universe's mechanics are still waiting to be rewritten? The cosmos is endlessly complex, and clearly we are only getting started. Thanks so much for joining me, and keep your curiosity alive.